On slide 41, I turn to the Monte Carlo simulations of cycles that were presented in the paper. The paper gives tables with the simulation results for 3 different kinds of models. We have them listed here: the 2-level random DSEM, the bivariate 2-level DSEM, and a cross-classified DSEM. So we have then for the cycles coefficients a random case for the first model, a fixed case for the second, and fixed case for the cross-classified DSEM. And you can think of many more variations with random here, and you can also think of cross-classified RDSEM, putting the cycles on the within level. So many more simulations that can be done. But what's interesting here in general is that each of these cases, each of these Monte Carlo studies uses 2 steps in the Monte Carlo. And that's really representing a general approach that you can use in many other settings as well when you do Monte Carlo studies. So you create some of the variables in step 1 and some of other variables in step 2 using define. And this 2-step approach, the general features of that is described in the user's guide in chapter 12. So let's take a look at the first model then. So it's a 2-level random RDSEM model. So that corresponds to figure 6 of the paper, not this Webtalk, but in the paper. So it has random effects, random coefficients for the cycles variables. And let's take a look at the details here. Monte Carlo names equals PA for positive affect, and this is the variable we want to generate. But then we also generate SX1 and SX2. And what are they? Well, they are the names for the random coefficients for x1 and x2. So random slopes, S as in slopes. Now we're going to work with 500 replications, and the cluster sizes are 256, which means 200 people and 56 time points. So corresponding to the data that we have looked at here in the Webtalk. Cluster sizes, number of different cluster sizes is 1, 56 for everyone. We have a lagged variable, and we want to save all of these 500 replications, the data sets that we generate in this fashion here. We have this star asterisk feature to represent that we do 500 of these data sets. And we're going to declare SX1 and SX2 as between level variables. And the question is, how do we generate them? Well, let's take a look at it. We do a 2-level analysis using base. And here we set B iterations to 200. You could do FB iterations also if you wanted instead, which signifies that we don't need complete convergence here. It would take a while to do the complete convergence for all 500 data sets, although that could be an interesting run as well. But we only need to generate the data, so we don't need to have perfect estimates. It's the data set that we're after. So then let's look at the model population here then. Here we specify hat variables, so residual variables. So we're looking at the residual relationships for PA over time. And the values, by the way, here in the right column come from one of the real data runs. And you have a residual variance here as well. That's obviously not the full model, but that's what we're going to do in step 1. And on between, we're going to work with the between part of PA. So that's the random intercept. And we're going to let it correlate with the random coefficients. And the random coefficients are allowed to correlate among themselves as well. And then we give them means for these coefficients, the mean of the random intercept and the two slopes. And then we give variances here as well. So what we're doing here is generating, according to this model, every variable that is not time related. The time related variables come in step 2. So now we get to step 2, and again the general features of a second step Monte Carlo run are given in the user's guide, chapter 12. So the data then is given like this. We have the file that was generated in step 1, and we specify that the data type is Monte Carlo. So we have a whole set of 500 data sets to go through. We're going to do 500 analyses. So the names list now, that comes the order of the variables is presented at the end, at the bottom of the step 1 run. So you have the SX1 and SX2 variables. So these are variables now, varying on the between level. And you have the PA variable, and more importantly, you have the time variable here. A time variable gets saved from step 1, ranging from 1, 2, and up. So then you have, as use variables, PA, X1, and X2. Cluster equals ID, lag 1, and we have the cycles on the within level, as we usually do in 2-level analysis. So that time variable then comes back into play in the define statement for X1 and X2. Time sits here. And now we create the real PA variable, the full PA variable. In step 1, we only generated the residual PA variable through the hat statement. And it was read in up here in the name statement rather. Here are the random coefficients, the vary across individuals, multiplying X1 and X2. So that's where you see that you have random coefficients. It's not fixed values, but actually a variable. And in the other examples, we're going to see that they are replaced by values, actual coefficient values. So then you do a 2-level random run. And here now you have a more substantial number of base iterations. And then we have the model here. So here now you specify random slopes for PA on X1 and PA on X2. We use the same name as in the data set here, but these are not the read in variables. These are coefficients, random coefficients that the analysis are going to determine. Then here is the PA on PA ampersand 1, sorry, hat 1. So that's a residual relationship. So these two lines in the model statement are the same as in step 1. So PA has been generated with these values. And then come all the between values here that are also from the same as in step 1, so that we are giving the true values in the Monte Carlo to which estimates will be compared, and the true values are those that we gave in step 1. Step 2 is sometimes called external, the external Monte Carlo step. So here you have it. That's the 2 steps of the 2-level random DSEM. Let's turn to the second model. Slide 44. So we have a bivariate 2-level DSEM, and here we don't have random coefficients. So this is like our prologue model on slide 5, but with fixed coefficients. So let's take a look at step 1. We have the same setting with 200 people, 56 time points. Now we bring in a second variable, tired, and that's lag 1. Should be a parenthesis instead of that 1. And we do the rep save, and once again we don't ask for complete convergence. Model population, here are the residual relationships that we generate, and here are the values for the variances, and then the between model where covariances, means, and variances are given. And as always, we'd like to have the same model as model population, so I don't repeat that. So then step 2. So once again, then in step 2, we read in the data set that was generated in step 1, type equals Monte Carlo. And here we have then, once again, the names list with the variables plus a time variable that's been generated. And we're going to use these variables, PA, tired, and the sine cosine variables that we create in the run here. And so in define, you have the usual x1, x2 with time coming from the names list up there. And here, PA, the full PA, the residual of PA that we generated in step 1, and then the fixed coefficients, no longer a variable, multiplying x1 and x2. And those values are taken from a real data run. Similarly, tired has fixed coefficients taken from a real data run, and adding the tired residual. So that's how you can compose the full model that you're interested in, the full variables that you want to generate and analyze. So then analyzing them, we have the model. We have here PA on x1. That value is the same as what we used to create it. So we know what the population value is. And same thing for x2. Here we have the autoregression for the same variable, the residual, and here is that key residual relationship, which was specified also on in step 1, etc. Nothing new then really here in step 2. So let's look at the final model, the third model. So now we're looking at a cross-classified DSEM model. So that's the model on slide 11 in this Webtalk, with the cycles on the between time level. So we're looking at a fixed coefficient case. So we aspire only to generate a y variable here, a single variable. And in cross-classified DSEM, we set up the cluster sizes a little bit differently, but you recognize the 200 people, 56 time points, and then you put 1 in parentheses here, and number of cluster sizes, you write like this. I'm not going to go into those details, but this does the job for me here. 200 subjects, that's level 2B. In the cross-classified language, and time points is level 2A in the cross-classified language. And we're going to do saving of all of those data sets that we generate, all of those 500 replications. And we do cross-classified analysis, and this is the same as before. And we do a regression here, y on y ampersand 1 on the within level, and on the between level we have the 2a, that's between time, so that's giving that variance here, and between 2b is between individuals. So note here then that the general notation for between time is level 2a, and that's what we need to use in Monte Carlo. We cannot have some other name. And between individuals, between ID is level 2B. So level 2A and level 2B should be stated here. On slide 47 then we have step 2, where we pick up the data, and now we have not only y but also time and some other variables, the ID and the lag1, which we ignore. So we have use variables y, x1 and x2, where x1 and x2 are created here, and we have two cluster variables, ID and time, and the between statement says that x1 and x2 are variables on the between time variable, and we generate x1 and x2 with that time variable. So time here is the same as time here is the same as time here, and we generate y as the fixed coefficients times x1 and x2 plus the residual y that we generated in step 1. So this is a cross-classified analysis, and we specify then the within model, the between ID model, and the between time model. And note here then that ID, this ID is the ID up here, and time is the time up here. So this step 2 is very much like a real data run in that sense. And that's why we can also use define in step 2. We can't use define in step 1. So here then on the between time level, you have the cycles on the between time level. This is the residual variance, and here you have the fixed coefficients sitting here, which were created over here. So that's how they were done, these analyses. And again, they represent a general strategy for dealing with Monte Carlo studies. You have more flexibility in the Monte Carlo studies if you take a two-step approach.